Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
All right, what in the world is thermal energy? So often when we talk about thermal energy, what we're doing is we're looking at thermal heat, right? It's so whenever there's any kind of energy transformation, a lot of heat is lost. We often say it's lost, but sometimes you can make use of it. So, for example, in an automobile engine, at least an internal combustion engine, there's a lot of excess heat. You ever touched the motor of a car after it's running, it's quite hot. And that heat, that's energy that could be used to move the car forward, but it actually just heats up the motor. In fact, in the car, you have a coolant system. There's antifreeze, and antifreeze cools the engine down so that the metal itself doesn't get so hot that it warps and ruins your engine. That will happen if you don't have enough coolant in a car. What we can do, though, is we can take that heat and we can put it into the cabin of the car if it's a cold day, and it can heat you up. So thermal energy is going to happen in any kind of a reaction. In fact, let's watch a short video clip that illustrates this. Hopefully you figured this out. It's not terribly rocket science. It's that there's going to be some energy when you have some friction. You've known this when you rub your hands together and you produce thermal energy. Turns out there are two equations for thermal energy. And actually, I'm not 100% that this is just two, but these are the two we're going to look at. The thermal energy equation could be the frictional force, like the video we just saw, times the delta X. So if you think about it, because the frictional force, for F of F, equals mu times the normal force, all right? Or you also might look at this. This is just force times distance, if you think about it, right? If you know what that frictional force is, times the distance that it's traveled, then you're going to get the thermal force. Now, also, there's another interesting one where this D is also a force. This is the drag force. So when a vehicle is traveling through air, all right, and it's traveling through air, there's a drag force that the air is opposing the motion of that. Now, the drag force is a complex equation. Here is the drag force equation right here, where we have the drag force, the D, if you will, is equal to 1/2. Notice it's kind of like 1/2, like mv squared. It has that kind of look to it, sort of. Half, of course, and then this is the coefficient of drag, which you get from a table like this, right? And you might notice that a racing cyclist, that's a relatively high number. And then this right here, this funny looking P, is the density of the fluid. So you have to have it in the density. So obviously, if I'm a swimmer and I'm swimming through a liquid, that's a much more dense liquid that I've got to overcome. A is the surface area, so it makes sense what's going to drag. This is why, aerodynamics, it's why pointy objects, the surface area as the wind comes over, it's like the tip of a airplane or something like that. If it's more tippy than if I have a big blocky airplane flying, then that's going to create more drag because there's more area that's going to get hit when it first hits. So that's area. And V, of course, is the speed squared. So all that said, let's see if we can do a question here. So this is the example. I'd like you to copy it down. How much energy is required for a 70-kilogram swimmer to complete a 1 kilometer swim at a steady speed here? We can say that the frontal area of a swimmer is this many meters squared, the drag coefficient for swimming in water, and the density of water. By the way, note here on the density, I didn't say this in the previous one, but the density is going to have to be in kilograms per meter cubed. You've got to keep everything's in kilograms. and meters. Earlier we said that the energy of the thermal energy is equal to the drag times the change in x. Now if you look at it, the change in x is 1 kilometer. So we know that this is 1,000 meters. I'm doing that conversion in my head. Everything's to be in meters, right? And now we have to use this fancy drag equation, right? The drag equation is 1/2 the coefficient of friction times the density times the area times the velocity squared. So we simply have to plug in our numbers. So this will be 1/2 times the coefficient of drag. In this case, this is this 0.08 number, times the density, that's this number here, times 1,000, times the surface area of the swimmer, which was, I did that, hold on, that was the frontal area. The coefficient of drag was 0.45. They're still multiplied. I've got these two in the wrong space, but they're all multiplied. Times the velocity, he's swimming at 1.4 meters per second squared, and you come up with 35 newtons. That all adds up to 35 newtons. And then we'll take 35 newtons, and we're going to plug it into here. So I would say 35 newtons times 1,000 meters equals 35,000 joules. So that's how many joules, how much heat, I should say, that the water will warm up, all right? Or that's the amount of energy that will be transferred into the water. And if you want to figure out how much energy that goes, now if you've taken like AP chemistry or something like this, they might have taught you this. There's another equation that says you can find the energy. It's just energy thermal. There's another equals M times C times delta T, where M is the mass of, in this case, the water. If it's a lake, it's going to be a massive number, times the C is the specific heat, and you can find out by how much the temperature will rise. Probably it's going to be, if you're swimming in a lake, because M is going to be so big that the delta T is not going to be that high. But that's where the energy is going. The energy is, well, it's not just going to the water. Some of the energy just goes to heat up the human. But most of it, I'd say 90% of it's going to the temperature. So you could actually find out how much increase the lake had if I knew the mass of the lake. But anyways, the idea, thermal energy, you've got your two equations. You'll be asked to do a couple of problems that relate to this. And yeah, Houston, we don't have a problem. We'll see you in class.